Hello everyone, my name is Ankush Kumar, and before I start talking about artificial intelligence, I want you to imagine something very simple. Imagine you wake up tomorrow morning, pick up your phone, and suddenly realize that everything related to AI has just disappeared. No ChatGPT, no Cloud, no Midjourney, no Gemini, no AI assistant videos, no AI voiceovers. Everything related to AI has just disappeared. Now think about it, how it would affect our lives. Students wouldn't be able to get instant explanations. Programmers wouldn't be able to do their programming and check their programming codes. Hospital would collapse as well. Everything related to AI would just collapse. This just technically shows that how easily and how dependent we humans are on artificial intelligence. But here is something more interesting. Even though millions of people use AI every day, but very few know what AI actually means. Some people think that AI is just ChatGPT. Some people think that AI is a robot. Some people think that AI is just a smart computer. But nothing actually defines what artificial intelligence actually is. So in this video, we're gonna learn everything about artificial intelligence, not from coding, not from mathematical equations, but from everything that has happened in the past and how artificial intelligence is actually working right now. We're gonna learn everything about artificial intelligence, such as neural networks, why they were made, how they are used, weight, biases, and many other things. Now let's begin with a simple question. What is intelligence? Because before we understand artificial intelligence, we have to understand intelligence itself. Let's begin with a 5-year-old child. When a 5-year-old child touches a hot cup of tea, they doesn't know that it's hot. They touches it, it hurts somewhere. Then from the very next time when they'll see steam coming out of a cup, they're just gonna be more careful. That is what we call learning from experiences. Now take a dog for an example. When we teach our dog to sit and give them a treat afterwards, and if we repeat that again and again, then after some time, they're gonna learn the pattern and they're gonna understand when you tell them that you have to sit now. That is also what learning from experience is. The dog is not reading any kind of article, the dog is not having any kind of programming in him. It's just he's learning from experience. Now take yourself for an example. Think of it as something that you started to learn how to ride a bike. Now you may fall many times, you will fall many times, but after enough practice, balancing become natural. That is what learning from experience is. If you understand, intelligence is not something which we call learning from books or anything. It's about learning from experience. So that is what actually intelligence is. Learning from experiences, learning from hit and trial methods, learning from seeing and understanding what is happening in our environment. That is what intelligence really is. Now, here's the exciting part. Scientists begin asking this one simple yet fascinating question, that if humans and animals can learn from experience, can machine do that too? This one simple question led to one of the biggest revolution in technological industry. This is where artificial intelligence begins. Now, artificial intelligence or AI is a field of computer science in which we humans create systems or technology that can perform tasks which includes human intelligence. Now, here's something we have to understand. We are not creating a machine or a system that can think like a human. We are trying to create a system that can perform tasks that includes intelligence. Now, that task can be recognizing faces in a photo, understanding spoken language, converting one language into another language, driving a car, detecting a disease from a medical scan, writing a computer program, or even having a conversation like this. like the one I'm having with you right now. At this point, you might ask another question that if AI is about making computer intelligent, then why can't we ask computer or exactly tell computer what they have to do? Which is a very simple and a very good question. And to answer it, let's take a very simple example. Think of it as something that your friend asked you to create a program where you have to find whether an email is a spam or not. So you might write rules like that if the sender is suspicious, mark it as spam. If the email have words like win or money, mark it as spam. Or if the email has too many links in it, mark it as spam, which might work on some email. But what will happen if the sender changes the wording? What will happen if they use congratulations, you have been selected instead of win or money? But if they uses image instead of text? But if they deliberately misspell some words? Now your working program has suddenly crashed. Every time someone invents a new trick, you have to update your program. Otherwise, that will not gonna work. But imagine doing this with millions of emails every day, which is impossible. So scientists realized this one thing, that rather than teaching computer every possible rule, why can't we just let the computer learn every possible rule by themselves, just like a child learns from experiences. So rather than teaching the computer that this is rule 1, this is rule 2, why can't we just show the computer thousands or millions of examples from which they will understand that yes, this email is a spam, this one is not, this one is genuine, and this one is a spam as well. After seeing enough examples, machine starts noticing the things that even humans might miss. That's the only difference, that's the major difference between traditional programming and modern AI. In traditional programming, human used to write rules. In modern AI, human provide examples, machine is the one who discovers the rules. That simple change completely transformed the world of computing. And after scientists realized this, they started asking this one question, that how can we build a computer or how can we build a machine that can learn from experiences? And to answer that question, we need to travel back in time. And that is where the real history of artificial intelligence begins. So now we know what artificial intelligence actually means. But here's one simple question that many people may have. Who invented AI? Was it OpenAI? Was it Google? Was it Microsoft? Or did AI begin with just ChatGPT? And the answer to that is none of them actually. So the story of artificial intelligence began long before ChatGPT, long before Google, and even before proper first modern computer existed. So to understand about artificial intelligence, we have to go back somewhere around 100 years. And like many other great discovery, it also started with one simple question: can a machine think? Today, this question might sound normal because we use AI every day. But imagine asking this question in 1940s. At that time, computers couldn't even display images. Most of them filled entire rooms, and they were only capable of doing mathematical calculations. So the idea that one day machine could recognize faces, understand languages, or even have a conversation sounded completely impossible. But there was one man who looked at machines differently. His name was Alan Turing. Alan Turing was a British mathematician and one of the pioneers of computer science. During World War II, he played a major role in breaking Germany's Enigma code, due to which Allied forces were able to decode secret military messages. Now, many historians believe that his work shortened the war and saved countless lives. Now, after World War, Turing started thinking about one simple question. He wondered if machines could perform all these mathematical problems, could machine perform tasks that include intelligence? Now, this was a revolutionary idea. At that time, machines were only seen as giant calculators. But Turing imagined something bigger, something different. In 1950, he published a paper called Computing Machineries and Intelligence. Instead of asking, can a machine think? He proposed a practical way to test intelligence. This began to known as Turing's test, by the way. Imagine you are sitting in one room with a computer keyboard, and in another room there are two participants. One is a real human, and the other one is a machine. You can only communicate by typing messages. You ask questions, both replies. Now, after a long conversation, if you cannot reliably tell which one is a machine, then that machine is considered intelligent in that specific sense. Notice something interesting here. The Turing test doesn't ask you to tell whether a machine has emotions or not. It asks something much simpler, that can a machine be this intelligent that it is impossible for a human to distinguish. Now, the Turing test remains one of the very best ideas of AI. But at that time, it was still just an idea. No one knew how to build such a machine. But then came one of the very most important year in AI history, the year 1956. At that time, in Dartmouth College, one of the very fine scientists gathered for a summer research workshop. Among them, there were researchers such as John, Marvin, and Cloud. Their goal was ambitious. They believed that if intelligent tasks could be described precisely enough, then eventually a machine should also be able to stimulate it. Now, during that workshop, John came up with a new term, and that term was artificial intelligence. This was the first time AI became an official field of research. Now, many researchers were really very optimistic. Some even believed that creating human level intelligence might just gonna take few more decades. Looking back today, we all know that they underestimated the challenge. Now, creating intelligence is far more difficult than anyone expected. But still, that conference gave birth to an entirely new and a totally different scientific field. In late 1950s and 1960s, researchers focused on now what we call symbolic AI. The basic idea was really very simple, that humans solves problems by following logical rules. So maybe computers can do the same. Imagine teaching a child how to identify a triangle. You might say a triangle has three sides, a triangle has three corners. So if a shape satisfies these conditions, then it is a triangle. Symbolic AI worked in a similar way. Humans manually wrote many rules into the computer. If that happens, do this. If that happens, do something else. Now, that worked surprisingly well for specific problems. Computers were able to solve algebraic equations, play simple games, prove mathematical equations, and answer questions in a limited situation, obviously. Now, people became excited again. Many thought that true AI was just around the corner, but then the reality arrived. Now, imagine trying to teach the computer how to recognize a cat only using rules. Now, you might write that cats have four legs, cats have ears, cats have fur, or cats have tails. But what about a cat sitting, a sleeping cat, a black cat in the dark, or a cat hiding behind a sofa, a kitten, a lion? Suddenly, the rules becomes countless and endless. The scientists realized something very important, that the real world is really very messy. It is impossible to describe the world using handwritten rules. Now, this became one of the biggest limitations of symbolic AI. Now, since at that time computers were really very slow and had very little memory capacity, due to which progress became dramatically low. Now, government and companies that had invested in AI uh, became, I would say, disappointed. Funding started disappearing. Researchers left the field. Even people s- stopped believing in promises, I would say. Now, this period started to known as the first AI winter. And just like winter slows down the growth of the plants, The AI winter slowed down the growth of AI research. The field struggled a lot for years. Just when everyone thought that AI had reached its dead end, at that time, another idea emerged out of nowhere, which was nothing but a very simple thing, that instead of programming intelligence, what if we could make the computer learn by itself? Not by writing millions of rules, but just by letting it learn through experience. Now, surprisingly and interestingly as well, this idea wasn't entirely new. Back in somewhere around 1957, a psychologist named Frank Rosenblatt proposed a term called perceptrons. Now, perceptrons was heavily inspired by human brain. It was an incredibly simple mathematical model that could take several inputs, perform tasks, and give the output as well. Now, at this time, it might sound ordinary, but at that time, it was revolutionary. For the very first time, scientists weren't making something in which you have to write all the programs and rules by yourself. They were trying to create something that can run by their own. Now, perceptrons had some serious limitations. In somewhere around 1969, two very famous and great researchers published a book showing that single layer perceptron isn't enough for many important problem solvings. And they introduced a very famous example called the XOR as well. Now, many people misunderstood that. Instead of concluding that single layer perceptron isn't enough, they concluded that neural networks themselves were a dead end. Research funding dropped again. This led to another difficult time for neural network research. However, a small group of scientists refused to give up. They realized that the problem wasn't the idea of neural network, but that the problem was that they weren't deep enough and nobody yet knew how to train larger networks efficiently. The real breakthrough would come with the rediscovery and the practical use of backpropagation in 1980s. Now, this would completely change the future of artificial intelligence. Because from that moment onwards, neural networks were no longer just an interesting experiment. They became machine that could actually learn. That is exactly what we are going to explore next. What is neural network? How does it learn? Why do people say it is inspired by the human brain? And why has it become the foundation of almost every AI that we use today? Let's find out. So now that we know how artificial intelligence started, researchers wanted to create a computer that can solve problems the way humans do. So at first they tried something very simple. Rules. If this happens to this, if that happens to that. And for simple problems, it somewhere worked. But then they discovered a major problem. Let's take a simple example. Imagine we want a computer to recognize an apple. We can tell the computer that an apple can be round in shape, or it can be red, it can be yellow, it can be green, or it has a stem. It sounds easy, right? But what happens when we show it a half green apple, or a sliced apple, or an apple covered by leaves, or a brown apple? Suddenly our rule start failing. So we add more rules and more and more. But no matter how many rules we write, there will always gonna be some new situation that the computer hasn't seen before. Now compare that with a child. We don't teach a child every possible rule about an apple. We just simply show them that this is an apple and this is also an apple. A red one, a green one, a big one, or a small one. And after seeing enough examples, the child learns from the pattern. Now, this gave AI researchers a brand new idea, that what if we stopped programming every rule and instead taught computers using examples? So instead of programming intelligence, what if we could teach intelligence? Now, this idea led towards neural networks. But now comes a very simple and a very big question. How does a neural network actually make a decision? Now, to understand that, we have to understand the very basic building block of neural network, which is perceptron. Now, a perceptron is essentially a simple artificial neuron. One single perceptron cannot build something like ChatGPT, but many, or I would say a large amount of artificial neurons working together can form a very powerful neural network. Now, let's understand one. Now, imagine you're hiring a software engineer and the candidate has 6 years of experience, a programming score of 90, and a communication score of 75. Now, these are what we call inputs. Inputs are simply the information that is entering in the perceptron. Now, here comes a very important question. Are all the inputs equally important? Of course not. For a software engineer, programming might matter much more than communication. Now, here comes the perceptron. The perceptron divides or gives every input different level of importance, and that is what we call weight is. A larger weight means that this information is more important. A lesser or a smaller weight means that this information matters less or doesn't matter that much. Now, during the training period, a neural network learns about these weights using example. But there's one more important component: bias. Now, bias is basically a value that shifts the result. Think of it like a starting push. A positive bias can push the result upward, and a negative bias can push it downward. So now we have three things: input, weight, and bias. And we combine them using one simple equation, which is like this. Now, don't let the formula scare you. It is simply saying that take each input, multiply it by its weight, add everything together, and then add the bias. Now, let's see it with numbers. Our candidate has a 6 years experience, a programming score of 90, and a communication score of 75. And our perceptron has learned that the experience weight is 4, the communication weight is 2, and the programming weight is 8, and the bias is minus 50. So now using the formula we know, we get z is equal to 6 into 4 plus 19 into 8 plus 75 into 2 minus 50, which gives us 24 plus 720 plus 150 minus 50, which is 844. So our perceptron's final weighted amount or final weighted result is 844. So we got our final number, 844. But here's something important. What does 844 actually mean? Is it a good score, or is it a bad score, or should the candidate be hired? And the answer of that question is even the perceptron doesn't know about it. Remember, now all we have done till now is combine the weight, the bias, and the inputs. Now we haven't made any kind of decision yet. But neural network isn't just something which helps us to create the numbers. It helps us to convert those numbers into decision. So let's make this example a little more simpler. Imagine that we decide that if the score is greater than 500, then hire. But if the score is less than or equal to 500, then don't hire the candidate. Now, in our scenario, our perceptron has produced 844, which is obviously greater than 500. So the answer becomes higher. Now we have converted a mathematical calculation into a decision. But here's an interesting part. Why do we need an activation function? Why can't we simply say that if the number is above 500, then the output is 1, and if it is less than 500, then the output is 0? Actually, this is how perceptron used to work earlier. They could use the threshold. If the result crosses a certain value, then the neurons activates themselves. But if it doesn't, then the neuron stays inactive. It is more like a yes or no this situation, or we can say an on or off situation as well. But real world problems aren't that simple. Imagine you are trying to recognize an apple. The computer might get the information like its shape, color, texture, or the type of size it is, and many other features. These features doesn't always have a simple yes or no relationship. A round shape might increase the possibility of something to be an apple, or a certain color can increase it, or a certain pattern can decrease it as well. So we need better understanding to create a better result, I would say. That is where activation function helps us. Now let's zoom out a little. Till now we've been talking about one single perceptron, but think about many perceptron working together. Think about hundreds of perceptron, or thousands of perceptron, or millions of perceptrons working together. And that is how a neural network actually works. One neuron might respond to one simple pattern, another can respond to something completely different. Now, when these neurons work together, the network can recognize and solve much more complicated patterns. And this is how neural networks becomes much more powerful. Now let's go back to our apple example. Imagine we give an image of an apple to a neural network. At first, it don't understand that this is an apple because it is receiving numbers representing information from that image. Now, some neurons might respond to simple edges, some might respond to shapes, some might detect patterns. As we go through deeper into the internet, these simple information can be combined, and eventually these information helps the neural network to resolve, or to help us to detect or solve more complex patterns. And once the network has combined all these patterns, it can finally make a prediction. For an example, we can say that after combining all the information from the image, the computer might predict or say that yes, this is an apple. And that is the basic idea. The network takes the information, it processes it through the neurons, and then gives us an output. But here comes a very basic and a very simple question, but also a very important one. How does the network know which weight should be used in the first place? Now, remember our example. We decided that experience has a weight of 4, programming has a weight of 8, and communication has a weight of 2. But in real neural network, who decide these numbers? And the answer is neural network learns these from the data. We cannot manually write, or we cannot manually set millions of weights one by one, but instead we give the network examples and let it adjust the weight during the training period. Imagine we are training a network to recognize apples. We give it an image, and it will look at it, and it might say that yes, this is an apple, which is totally correct. But sometimes it can get it wrong, and it can say that this isn't an apple. But now the network knows that something is wrong and they have to do something. The network can adjust its weight based on its mistakes. Maybe one weight needs to be a little larger, or maybe another needs to be, I would say, a little smaller. After doing all this altering again and again, the network predicts the answer again, and then it checks how close that answer was to the correct answer. And eventually, after doing this again and again, gradually the network becomes good at making prediction. And this is the major shift we were looking for. Earlier, researchers were trying to tell computer exactly what to do. They were writing rules. But the introduction of neural network gave us a totally different approach, that instead of writing every possible situation or every possible outcome, why can't we just give computer an example and let it learn through the data? And that idea completely changed the direction of artificial intelligence. But remember one simple thing: one perceptron is still very limited. The real power comes when we add or merge or connect many artificial neurons together. And that is what we're going to explore next. So, in this video, we covered things such as artificial intelligence, a neural network, perceptron, weight, bias, and many other small stuffs. But I would say it is still the very beginning. In the next video, we will be discussing things such as the layers of neural network, cost function, activation function, and many other things. So if you genuinely want to understand how things work inside a neural network, make sure to check the next video as well. And I'm gonna see you there. Thank you.